A cat can be both alive and dead inside a sealed box. This is not a magic trick, but a cornerstone of quantum mechanics, a realm where particles exist in multiple states at once. Now, stretch that bizarre logic to its absolute limit. What if the entire universe began in such a state, a single moment where reality itself was both here and not here, something and nothing? This is the concept of the universe's very first quantum superposition, the primordial flicker from which everything we know emerged. We are about to explore 30 distinct theories that attempt to explain this ultimate origin event. By the end, you will possess a sweeping understanding of how our cosmos might have bootstrapped itself into existence. We will investigate if our universe is one of many in a cosmic birthing pool, and whether a conscious observer was needed to bring it into being. What does it truly mean for reality to begin? The first theory takes us to the absolute brink of nothingness. Picture not an empty space, but a true void, a realm of pure potential where even the concepts of here and there, before and after, have no meaning. In this ultimate nothing, a strange and fundamental rule of quantum mechanics comes into play. Nothing is ever perfectly still. At the tiniest imaginable scales, there is always a seething, restless energy, a constant flickering of particles and forces popping in and out of existence. This is the quantum foam, the fundamental fabric of reality itself. From this eternal sea of potential, a fluctuation of unprecedented scale occurred. It was not a single state, but a superposition, a state where the void was both perfectly empty and yet contained the entire potential for a universe, all at the same time. This was the moment of Genesis, a single, impossible quantum fluctuation that refused to immediately cancel itself out. In that fleeting instant, the superposition of nothing and everything held. The wave function describing this state of reality did not immediately collapse. Instead, it lingered, and in that lingering, a new possibility was born. The fluctuation grew, stretched by forces we are still trying to understand. And in that expansion, the superposition resolved, giving birth to the single, tangible timeline of our own cosmos. The universe did not come from a single point of matter, but from a single, improbable question posed by the void itself, a question whose answer was everything we see. That single, fleeting flicker from the void introduces a staggering possibility. What if our universe was not a lone miracle, but one birth among countless others in a cosmic nursery? This is the second theory, the multiverse birthing pool. Picture an eternal, infinite landscape, a pre-existing reality where the fabric of space-time is constantly stretching and bubbling. In this environment of eternal inflation, new universes can sprout from the quantum foam like bubbles in an infinite, boiling ocean. Each of these budding universes begins not as a definite thing, but as a quantum superposition. It is a potential reality, existing in a state of all possible initial conditions, all possible laws of physics, all at once. This is the birthing pool, a vast quantum sea of unborn worlds. Our own universe was once just one of these shimmering possibilities, a specific superposition of being a universe with certain properties. How did it become our tangible reality? This is where a profound interpretation of quantum mechanics enters, the many worlds interpretation. It suggests that the wave function describing this superposition never actually collapses. Instead, every single possible outcome contained within that superposition becomes real. In this view, our universe did not get selected. It simply branched off. At the moment of its inception, the superposition of all possible universes decohered. One thread of possibility became the world we inhabit, a universe with three spatial dimensions and the specific physical constants we measure. But every other thread became real too, each one an entirely separate universe within a greater multiverse. In one branch, gravity might be a repulsive force. In another, light travels at a walking pace. Our entire cosmic history is just one path taken from an infinite set of possibilities that were all equally real in that first primordial moment. The question then shifts from how our universe began to why we find ourselves in this particular one, a line of inquiry that leads us to an even more mind-bending frontier. The idea of a cosmic birthing pool is dizzying, but it raises a fundamental question about the very substance of our reality. Are the three dimensions of space we experience truly fundamental, or are they merely an illusion projected from a simpler, more basic reality? This leads us to the third theory, the holographic principal origin. It suggests our universe, and its very first quantum state, emerged not from a point, but from a surface. Imagine the information that defines everything in our three-dimensional world. Every galaxy, every person, every law of physics is actually encoded on a distant, two-dimensional boundary, like a cosmic DVD. Our rich, three-dimensional existence is merely a projection from that flat surface, a hologram of staggering complexity. In this framework, the universe's first quantum superposition did not happen in the volume of space we know. It happened on that two-dimensional boundary. The information describing the initial state of everything was not in one configuration. It was in a superposition of all possible initial configurations, a blur of every possible way the universe could start, all encoded simultaneously on that foundational surface. This blur of information on the boundary then projected upwards, creating the three-dimensional superposition we have been discussing, the state of being both something and nothing. The collapse of that superposition, the moment our specific timeline crystallized, corresponds to a specific set of information being selected or stabilized on that two-dimensional screen. In a sense, the Big Bang was not an explosion in space, but the moment the cosmic projector was turned on, translating a shimmering, uncertain code into the tangible reality we now inhabit. But what if the beginning was not a true beginning at all? The fourth theory, cyclic conformal cosmology, proposes a universe without a definitive start or end. Instead, our cosmos is part of an endless cycle of death and rebirth, a cosmic phoenix. In this model, the Big Bang was not the absolute genesis, but merely the latest turn in an infinite wheel. Picture a universe expanding to its maximum size, all matter and energy stretched to an impossibly thin, cold, and featureless state. It is a universe that has, for all intents and purposes, died. But in this state of maximum dilution, a remarkable transformation occurs, a conformal rescaling. This is a mathematical reset button for reality itself. All distances and durations are effectively remapped, losing any absolute meaning. The vast, cold, aged corpse of the previous universe is rescaled to become the hot, dense, and youthful seed of the next. In this transition, the quantum state of the universe is not created from nothing. It is inherited, the final, fading quantum superposition of the old cycle, a blur of its ultimate possible states, becomes the initial quantum superposition for the new one. The universe's first quantum state, as we perceive it, was not a single flicker from the void. It was a transfer of existence, a legacy passed from a forgotten predecessor. That primordial superposition, where reality was both something and nothing, was simply the moment the cosmic wheel completed its latest revolution, resetting the stage for a new act in an eternal play. This theory erases the need for a single mysterious beginning, replacing it with an endless, rhythmic dance of cosmic information, forever recycling itself into new forms. Sir Roger Penrose offers a different kind of cycle, one not of repetition but of profound transformation. His conformal cyclic cosmology, or CCC, envisions a chain of cosmic epochs called eons, each beginning with its own Big Bang and expanding out into an infinite future. The end of one eon becomes the birth of the next through a beautiful, almost magical, mathematical transition. When a universe has expanded to a state of near nothingness, populated only by massless particles like photons, something incredible happens. All notions of distance and time lose their meaning. In this conformal boundary, the infinite, timeless end of the old eon is geometrically identical to the hot, dense, timeless beginning of a new one. They are, for a moment, the same point. This is where quantum superposition enters in a breathtaking way. The final quantum state of the previous eon would not simply vanish. In its ultimate moments, as it approached that conformal boundary, its quantum states would become a blur of possibilities, a superposition of its final configurations. This fading whisper of a dead universe, this ultimate quantum question, is then mapped directly onto the blank slate of the new eon. The very first superposition in our cosmic history, that primordial state of being both something and nothing, was not a random fluctuation. It was an inheritance. It was the final, unresolved question of a cosmos that came before us, translated and reborn as the first moment of our own. In this view, our universe did not spring from nothing, but from the ghost of a previous reality, its quantum information preserved and reset across the boundary of time itself. The echo of a forgotten eternity is written into the fabric of our first instant. The ghost of a previous cosmos is a profound inheritance, but it still operates within a familiar framework of cause and effect. What if that framework itself is the illusion? The sixth theory shatters our most basic intuition, the steady flow of time. It proposes that time is not a fundamental stage on which the universe plays out, but an emergent property, a collective mirage born from countless quantum interactions. In this timeless view, the universe's initial state was not an event in time, but a single static object, the wave function of the universe. This is not a wave of probability moving through time, but the entire history and future of reality, all potentialities, encapsulated in one timeless mathematical entity. This universal wave function existed in a state of perfect superposition, containing every possible configuration of matter, every possible arrangement of particles, every possible history all at once. There was no before, no after, just an infinite, silent tapestry of what could be. So how did we get the flowing, dynamic cosmos we experience? The Big Bang in this radical picture was not a beginning in time. It was a decoherence event, a spontaneous breaking of the perfect symmetry within that timeless wave function. Think of it like a perfectly symmetrical ball balanced on the tip of a needle. It represents every possible direction it could fall all at once, in a state of superposition. The slightest interaction, a vibration in the air, causes it to choose one path, to fall in one specific direction. Our universe is that one specific fall. The moment of decoherence was the moment the timeless superposition of everything resolved into a single, consistent timeline. A single history that we now perceive as unfolding from a hot, dense past toward an unknown future. Time and the arrow of time itself emerged from this event, a story we are telling ourselves as we travel along one thread of that infinite, timeless tapestry. Our universe is born from a ghost, but a ghost needs a mechanism to build a cosmos. The seventh theory provides that engine, focusing on a single, all-powerful entity, the inflattened field. This was not a field of wheat or grass, but a field of potential energy permeating the newborn universe. In its first moment, this inflattened field did not have a definite value. It existed in a quantum superposition, a state of being many possible energy levels all at once. This was the universe's ultimate unstable foundation, a quantum spring coiled with every possible amount of tension. The collapse of this specific superposition was the trigger for everything. As the inflattened field's wave function resolved from many possibilities into one specific, high-energy state, it unleashed that stored potential in a single, catastrophic release. This was the moment of cosmic inflation, an expansion so rapid it makes a supernova look frozen in time. In a fraction of a second, a subatomic speck of space was stretched to a size larger than our entire observable universe. But the inflattened's quantum nature left an indelible mark. The very quantum fluctuations that defined its initial superposition, tiny differences in energy from point to point, were stretched to astronomical scales by the inflation they powered. These microscopic wrinkles became the seeds for all future structure. The subtle variations in the cosmic microwave background, the vast web of galaxies, the very spot where you are sitting right now, all trace their ultimate origin back to the quantum jitters frozen into the fabric of space during that first, fleeting moment when the inflattened field decided what it was going to be. This cosmic inflation, driven by a single quantum field, seems to have set the stage for everything we know. But what if that entire stage, including the play of cosmic history we believe in, is an illusion? The eighth theory presents one of the most unsettling ideas in all of physics, the Boltzmann brane paradox. It begins with a simple, almost undeniable fact about probability. In an eternal, mostly empty void, even the most wildly improbable events are not just possible, they are inevitable given enough time. A fully formed, self-aware brain could spontaneously fluctuate into existence, complete with a lifetime of fabricated memories, believing it exists in a real, structured universe. This is a Boltzmann brain. Now, consider the implications for our own origin story. Our entire observed cosmos, with its 13.8 billion-year history, its first quantum superposition, its inflationary expansion, and its vast web of galaxies, is an incredibly ordered, low-entropy state. The probability of such an intricate, structured universe fluctuating into existence all at once from a random quantum event is astronomically small. However, the probability of just a single, disembodied brain with the false memory of such a universe is vastly, unimaginably more likely. The paradox is stark. In an eternal void, you should expect to be a lonely, momentary brain hallucinating a cosmos, not a person inhabiting a real, ancient universe. So why are we here in this seemingly ordered reality? This directly challenges the validity of our cosmic origin. Our cherished narrative of a first quantum superposition leading to the Big Bang might not be the true history of a real cosmos. It could simply be the opening chapter of a detailed, but entirely false memory implanted in a brain that popped into existence a moment ago. The universe's first moment, as we understand it, becomes not a genesis, but a phantom, a convincing detail in a cosmic delusion. This forces us to question the very nature of our evidence. Is the cosmic microwave background a real echo of a hot, dense state, or just a perfectly fabricated part of the illusion? The search for our true beginning collides with a terrifying possibility that the most likely origin for any conscious experience is not a universe at all, but a fleeting and solitary lie. That terrifying possibility of a solitary, hallucinating brain forces a radical reassessment of all evidence. If our senses cannot be trusted, then perhaps the very laws of physics are not fundamental truths, but programmed rules. This brings us to the ninth theory, the simulation hypothesis. It proposes that our universe is not a base reality, but a sophisticated digital construct, a simulation running on a computer of unimaginable power in a higher-level existence. In this framework, the universe's first quantum superposition was not a mysterious fluctuation in a primordial void. It was the moment the simulation was booted up. The initial state of everything was simply the first line of code executed, or the moment a cosmic random number generator was activated to seed the virtual reality with its initial conditions. The Big Bang, in this view, was the initialization of the program, the allocation of computational resources to run a cosmos. The quantum superpositions we observe in particles today are not evidence of deep reality, but merely a reflection of the simulation's underlying programming, perhaps a method to conserve processing power by not calculating definite states until an observation is required. This digital origin story carries profound implications. If we are in a simulation, the quest to find a single, elegant theory of everything may be futile, because the laws of physics we are trying to unify might be ad hoc, cobbled together code not meant to be perfectly consistent. Glitches in the matrix, such as unexpected cosmic rays or strange statistical anomalies in particle data, could be traces of the underlying programming. The simulation hypothesis transforms the meaning of existence itself, suggesting our rich reality, with all its love and loss and discovery, is ultimately data in a vast computer, and our search for a first cause is just the search for the programmer's start button. The simulation hypothesis suggests a programmer, but what if we are the ones writing the code? John Archibald Wheeler proposed a universe that is not just observed, but brought into being by observation. This is the participatory anthropic principle, a radical rethinking of the relationship between life and the cosmos. In this view, the universe's first quantum superposition was not a momentary flicker. It was a state that persisted unresolved for billions of years. The initial wave function of everything remained a blur of all possible histories, all potential starting points, until a very specific, momentous event occurred. The emergence of the first conscious observers. You, me, and every other sentient being are part of a cosmic chain of witnesses stretching back to the first primitive life forms that could perceive their world. Our act of looking back in time, of measuring the cosmic microwave background, and reconstructing the Big Bang, is not a passive discovery of a fixed past. It is an active participation in its creation. The superposition of the universe's initial conditions collapsed retroactively, solidified by our present-day observations. We are not just living in a universe that allowed for life. We are living in a universe that required life to become definite. The specific laws and constants we measure, the very nature of that first quantum leap, were waiting in a state of potential until conscious beings evolved to select one consistent timeline from the infinite quantum haze. This idea turns causality on its head. The universe did not create us. We, through the act of observation, finished the job of creating the universe, reaching back across the eons to lock in its birth. This cosmic cycle of observation and creation presents a universe defined by its participants. But what if the stage itself is woven from a fabric of tiny, vibrating loops? Loop quantum gravity offers a radical new picture of space and time. proposing that the fabric of reality is not smooth and continuous, but composed of a web of finite, indivisible threads. In this granular universe, the story of the Big Bang is rewritten. It was not a singular, explosive beginning from an infinitely dense point, a place where our laws of physics break down completely. Instead, loop quantum gravity describes a cosmic rebound, a big bounce. Our universe was born from the collapse of a previous cosmos, a phase where all matter and energy were crushed together under immense gravitational pressure. But this compression did not lead to a true singularity. The quantum nature of spacetime itself acted as a cosmic repulsor. As the previous universe contracted to its smallest possible size, the intense quantum forces within the fabric of space caused it to spring back, expanding outward in the event we now call the Big Bang. At the heart of this bounce, at the moment of maximum compression, the quantum geometry of the universe entered a state of profound superposition. The very building blocks of reality, the loops of space and time themselves, were not in one single configuration. They existed in a blurred state of all possible geometric arrangements, a quantum foam of potential universes. This was not just a superposition of particles or fields, but a superposition of the very rules of the game. The way these loops connected and interacted in that critical moment determined the fundamental laws that would govern the new cycle. The strength of gravity, the number of spatial dimensions, the masses of elementary particles, all these properties were not predetermined. They were selected from a vast quantum menu of possibilities as the universe's geometry resolved from its blurred state into one specific, stable configuration. Our universe, with its 3 dimensions of space and 1 of time, is simply the one thread that was woven from that quantum tapestry at the moment of the bounce. The first quantum superposition was not of something in the universe, but of the universe's own operational code, crystallizing into the physical laws we now work to decode. The granular geometry of the bounce gave us our laws. But what if those laws are just one possible setting in a cosmic control room of almost limitless options? String theory, one of the most ambitious frameworks in physics, suggests that at the most fundamental level, everything is composed of unimaginably tiny, vibrating strings. The way these strings vibrate dictates the properties of every particle and force, from the electron to gravity itself. But this elegant idea comes with a staggering implication, a vast and sprawling landscape of possible realities. This landscape is not made of hills and valleys, but of different vacuum states, each one representing a unique, self-consistent set of physical laws and constants. In one valley, the strength of gravity might be 1,000 times stronger. In another, the nuclear forces are too weak to form atoms. The number of these possible universes is not just large, it is a number so vast it dwarfs the number of atoms in our observable cosmos. Within this framework, the very first quantum state of our universe was not a simple choice between something and nothing. It was a grand, overarching superposition over this entire landscape. Our entire cosmos began as a quantum blur of every possible set of physical laws, all coexisting simultaneously. It was a reality that was, in its first instant, both a universe with strong gravity and weak gravity, with 4 dimensions and 11 dimensions, with stars and without stars. The collapse of this immense superposition was the most critical event in our history. It was the moment a single point in the landscape was selected, locking in the specific vibrational patterns that would become our electron mass, our speed of light, and our cosmological constant. The fine tuning we observe, the seemingly perfect balance that allows for galaxies, planets, and life, was not designed. It was the result of a random quantum roll of the dice across an infinite array of possibilities. Our universe is not special. It is simply the one ticket that was drawn from a cosmic lottery of unimaginable scale. A single, stable harmonic frequency selected from a primordial chord of every possible note. This quantum dice roll across the landscape of string theory feels utterly random. But what if the birth of our universe was not a random selection, but a kind of agreement, a cosmic handshake negotiated across time itself? This is the 13th theory, rooted in the transactional interpretation of quantum mechanics. In this radical view, every quantum event, from a particle's path to the universe's origin, is a transaction. It begins with an offer wave, a ripple of probability that moves forward in time, announcing a potential outcome. This offer is then met by a confirmation wave, an echo that travels backward from the future, accepting the offer and sealing the deal. This backward and forward negotiation culminates in a handshake, a moment where reality solidifies. Now, apply this to the first moment of everything. The initial quantum superposition of the universe was not a single, blurry state waiting to be observed. It was a storm of offer waves, a chaotic burst of every possible way a universe could begin, all radiating forward from the precipice of time. These offers flew into the void of what would become the future, a spectrum of potential cosmic histories. From that future, confirmation waves traveled back, not from conscious observers, but from the sheer stability of the universe that would eventually form. The specific laws, the precise cosmological constant, the very fabric of space-time we now inhabit, were all stable enough to send a confirmation signal back to the beginning. The Big Bang was the moment of the handshake. It was the instant a specific set of offer waves, describing a viable, long-lasting cosmos, were met and confirmed by the echoes of their own future existence. Our universe did not simply pop into being. It was ratified. Its entire history, from the first quantum fluctuation to the formation of galaxies and life, was part of a single, self-consistent transaction, a deal struck between its own birth and its ultimate destiny. The first superposition was this entire negotiation process, a timeless dialogue that culminated in the reality we call home. That cosmic handshake required a final, decisive moment to become our reality. This leads us to the 14th theory, the crucial process of decoherence and einselection. In the quantum world, a particle can exist in a blur of states, like a spinning coin that is both heads and tails. This fragile superposition is maintained by isolation, but the moment that coin interacts with its environment, the air molecules around it, the table it might land on, the superposition is destroyed. The coin is forced to choose. This is decoherence, the process by which the quantum world gives way to the definite, classical world we experience. It is not a physical collision, but a leakage of information. The quantum system becomes entangled with its surroundings, and its once private superposition becomes a public fact, forcing it into one state. This is where einselection, or environment-induced superselection, comes in. The environment does not just randomly pick a state. It selects for states that are robust, that can withstand the constant interaction without being constantly disrupted. These are the pointer states, the classical outcomes we actually observe. Now, apply this to the universe's very first moment. The initial universal wave function was a perfect, pristine superposition of all possible beginnings. But what could possibly serve as an environment for the entire cosmos when nothing else existed? The answer may lie within the universe itself. In that unimaginably dense and hot state, different parts of the nascent reality could have acted as environments for each of them. The primordial quantum fields, like the inflatoned field, might have decohered each other. The fabric of spacetime itself, perhaps granular and foamy, could have provided the necessary interaction. This self-decoherence would have been incredibly rapid. The universe's own internal components, by interacting and becoming entangled with one another, forced the entire system to lose its quantum coherence. The environment selected for a stable, classical state from the infinite quantum menu, a state that could consistently support the unfolding of physics as we know it. The Big Bang, then, was not the moment of superposition, but the moment that superposition ended, selected by the universe's own chaotic, internal conversation. The birth of our classical world was a necessary loss of quantum innocence. This chaotic decoherence solidified our reality, but it begs a deeper question. What was the canvas upon which this first quantum decision was painted? The 15th theory dives into the raw, churning substrate of existence itself, the quantum gravity foam. At the very smallest possible scale, the Planck length, the smooth, continuous space-time we take for granted dissolves into a frenetic, probabilistic sea. This is not a calm ocean, but a boiling foam, where virtual particles pop in and out of existence, where microscopic wormholes constantly form and vanish, and where the very concepts of here and there lose all meaning. In this primordial chaos, the geometry of space-time is not fixed. It is a quantum superposition of all possible geometries, a blur of countless ways for the fundamental building blocks of reality to connect. Our entire universe, in this view, did not emerge from a singularity, but crystallized from a particularly stable and long-lived superposition within this eternal, frothing chaos. Imagine the quantum foam as a stormy ocean, with waves of every possible shape and size crashing into one another. Most of these waves are fleeting, lasting only for a minuscule fraction of a second before collapsing back into the sea. But one specific, incredibly complex wave pattern, a superposition of geometric connections, achieved a fragile stability. It was a self-reinforcing quantum state, a configuration of the foam that did not immediately dissolve. This stable bubble of structured possibility, this one coherent knot in the chaotic foam, was the seed of our cosmos. Its internal quantum state was the universe's first superposition, a specific, stable pattern of potentiality that managed to resist the surrounding turmoil. The moment this bubble decohered from the greater foam, the moment its internal geometry snapped from a blur of possibilities into one definite structure, was our Big Bang. The vast, expanding space-time we inhabit is not a void filling with galaxies, but the inflated, fossilized imprint of that one lucky, stable knot in the quantum foam, a single eddy that grew to become everything. That stable knot in the foam gave us a universe, but one of profound symmetry. In its earliest, hottest moments, reality may have been governed by a perfect and elegant balance known as supersymmetry. This theory proposes that every known particle had a hidden superpartner. For every quark, there was a hypothetical squark. For every electron, a selectron. These superpartners would have been identical in every way to their normal counterparts, except for one key property, their spin. In this state of perfect supersymmetry, the forces of nature were unified into a single, magnificent superforce, and the quantum state of the universe was a harmonious superposition, balanced between matter and its shadowy twins. But this perfect balance was tragically fragile. As the newborn universe expanded and cooled, it underwent a catastrophic phase transition, like water freezing into ice. Supersymmetry broke. The perfect harmony was shattered. The superpartners, once identical to the regular particles, acquired immense mass and vanished from the low-energy world we inhabit, leaving behind only the familiar, asymmetrical menagerie of particles we see today. This breaking of supersymmetry was far more than just the disappearance of hypothetical particles. It may have been the very event that collapsed the universe's initial quantum superposition. In that state of perfect symmetry, the properties of matter and forces were not fixed. They existed in a blur of possibilities. The act of supersymmetry breaking selected one specific, stable configuration from that blur. It locked in the masses of the quarks, the strength of the electromagnetic force, and the very existence of the Higgs boson. The universe we live in, with its specific, seemingly arbitrary constants, is a direct consequence of the particular way supersymmetry chose to break. We are not living in a perfectly symmetrical reality, but in the one fragment of that perfection that survived the Great Breaking, a cosmic echo of a lost harmony that defined our very first moments. A lost harmony of perfect symmetry gave us our universe. But what if that entire structure, the very stage of space and time, is built from something far more fundamental? Causal set theory proposes a universe of breathtaking simplicity at its core. Forget a smooth, continuous fabric. Reality is composed of a vast collection of discrete events, like grains of sand. These are the causal sets. Each event is a fundamental point of existence, and the only thing that truly defines them is their relationship to each other. A single, immutable rule governs this cosmic network. If one event can influence another, if a cause can lead to an effect, they are connected. This web of cause and effect is not laid out in space and time. It is what creates space and time. The illusion of a flowing, continuous reality emerges from the sheer number of these connections. The way this immense network of causal relationships grows and complexifies. In the very beginning, then, there was not a singularity, but a single, solitary event, the very first atom of spacetime. This primordial seed did not exist in a void, because there was no void for it to exist in. It simply was, and in its first moment, it was not a definite thing. It existed in a quantum superposition of all its potential futures, a blur of every possible causal connection it could ever make. It was a single question mark, pregnant with the potential for an entire cosmic history. The growth of this causal set was the birth of time itself. As new events were born from this seed, as the network of cause and effect expanded, the universe chose a specific path from that initial superposition. Each new connection solidified a piece of reality, forcing a definite past to crystallize from the quantum haze. The arrow of time we experience is not a fundamental law, but a direct consequence of this relentless, one-way growth of the causal set. We are not moving through time. We are witnessing the ongoing creation of time, as each new event is added to the immutable, growing history of the cosmos. Our classical, definite world emerged when the web of cause and effect became so dense and interconnected that the quantum blur of the beginning was permanently locked into a single, unchangeable story. That growing web of cause and effect implies a deep, underlying structure. But what if that structure is forged by the most intimate of connections? The 18th theory, the AR equals EPR conjecture, proposes a breathtakingly beautiful unity. It suggests that two of the most bizarre concepts in physics, wormholes and quantum entanglement, are not just similar. They are the exact same thing described in two different languages. An Einstein-Rosen bridge, or a wormhole, is a hypothetical tunnel through spacetime, a shortcut connecting two distant locations. The EPR paradox, named for Einstein, Podolsky, and Rosen, describes the spooky connection of quantum entanglement, where two particles, no matter how far apart, share a single, unified quantum state. The R equals APR conjecture boldly states that every pair of entangled particles is connected by a microscopic wormhole. They are not communicating faster than light. They are literally linked by a tiny bridge in the fabric of reality itself. Now, apply this to the universe's very first moment. The initial quantum superposition was not a simple blur of a single particle. It was an impossibly complex, all-encompassing state of entanglement. Every potential piece of the nascent cosmos was quantumly connected to every other piece in a single, unified wave function. This was not just a superposition of states. It was a superposition of connections. According to this conjecture, that vast, primordial web of entanglement did not exist within a pre-existing space. It was space. Each of those spooky quantum connections geometrically manifested as a tiny, wormhole-like thread in the emerging fabric of spacetime. The moment of the Big Bang, then, was the instant this cosmic tapestry of entanglement underwent a profound transformation. As the universe expanded and cooled, this perfect, all-encompassing entanglement began to decohere. The microscopic wormholes connecting everything began to pinch off, leaving behind the classical, separated spacetime we recognize today. The vast, empty distances between galaxies are not a void, but the fossilized remnant of a time when everything was directly, intimately linked. The first quantum superposition was the blueprint for the geometry of existence itself, a single, entangled thought that unfolded in the stage of space and time upon which we now stand. That cosmic tapestry of entanglement wove the very stage of space. But what about the director of the play, time itself? The 19th theory, the thermal time hypothesis, offers a radical answer. Time is an illusion born from heat. We perceive time as a river flowing from past to future, but this hypothesis suggests this flow is not fundamental. It is a side effect, a story we tell ourselves because the universe is in a particular kind of state, a thermal state. In the beginning, the universe's initial quantum superposition was a state of perfect order, a pristine and singular configuration of ultimate potential. There was no distinction between past and future because the state itself contained no inherent arrow. But as that first superposition evolved, as it began to interact with itself, it heated up. It transitioned from a state of pure quantum information into a hot, dense, and chaotic plasma. This was the moment the clock started ticking. The thermal time hypothesis states that the flow of time emerges directly from this thermal state. We do not move through time, we move through a universe that is out of equilibrium. The reason we remember the past and not the future is because the past was a more ordered state, and the universe has been becoming more disordered, more thermally mixed ever since. The Big Bang, therefore, was not just the beginning of space, but the ignition of the thermodynamic engine that creates the sensation of time's passage. Before that thermalization, in the first fleeting instant of superposition, the concepts of before and after were meaningless. There was no time, only a silent, frozen question. The birth of heat was the birth of history itself, carving a clear past and future from a timeless quantum blur. Our relentless march forward is simply the universe cooling down, a single, long exhalation from that first hot breath. Heat and time gave our universe its direction, but they leave a deeper mystery unresolved. What was the mechanism that actually collapsed the first, all-encompassing quantum blur into our single reality? Objective collapse models provide a startlingly simple answer. The wave function they propose does not need a conscious observer to collapse. It falls on its own. Theories like the Ghirardi-Rimini-Weber model, or GRW, introduce a fundamental randomness into the heart of quantum mechanics. They suggest that every particle has a tiny but non-zero probability to spontaneously and randomly collapse from a spread-out wave into a definite location. For a single electron, this event is so incredibly rare it might only happen once in many billions of years. But the universe is not made of one electron. It is made of an uncountable number of particles. When you have a near-infinite ensemble, these rare, random collapses become not just probable, but inevitable and frequent. Apply this logic to the universe's very first quantum state. That initial, pristine superposition of all possible beginnings was not stable. It was a ticking bomb. It contained within its wave function the potential for its own destruction. According to objective collapse, it only took one single, spontaneous, and random collapse event somewhere within that primordial quantum soup to set off a chain reaction. One tiny part of the wave function, representing one specific configuration of energy or geometry, suddenly snapped into a definite state. This single, random event broke the symmetry. It acted like a seed crystal dropped into a super-saturated solution, forcing the entire system to rapidly crystallize around it. The collapse propagated at lightning speed through the entangled hole, freezing the rest of the universal wave function into a single, consistent timeline. Our specific universe, with its particular laws and initial conditions, was not chosen by a god, a programmer, or a conscious being. It was selected by a cosmic coin toss, a single, objective, and utterly random quantum fluctuation that just happened to go one way instead of another. In this view, the birth of reality was not a gentle emergence, but a sudden, spontaneous, and objective shattering of infinite possibility into one concrete fact. That spontaneous collapse was an objective, mindless event, a random shattering of potential into fact. But what if the exact opposite is true? What if the quantum world is not a realm of objective randomness, but a deeply personal one, shaped by our individual perspectives? This is the 21st theory, quantum Bayesianism, or cubism. It makes a startling claim. A quantum state is not a description of an objective physical reality. It is a personal belief, a user manual for an agent navigating an uncertain world. When a physicist assigns a quantum state to a particle, they are not describing the particle itself. They are encoding their own personal expectations, their own degree of belief about what will happen when they interact with it. The famous Schrödinger's cat is not objectively both alive and dead. The wave function is simply the best guess of the person outside the box, based on the information available to them. Opening the box is not an observation that collapses an objective reality. It is an experience that forces the agent to radically update their personal beliefs. Now, take this deeply subjective view and apply it to the ultimate beginning. The universe's first quantum superposition was not a physical state of the cosmos. It was the first guess. It was the initial, personal belief of the very first agent to interact with the nascent reality. Who or what was this agent? It could have been a fundamental entity within the cosmos itself, a primitive form of consciousness, or perhaps something entirely beyond our current understanding. This agent started with a blank slate and made a guess, a probability assignment about what would happen next. This first belief, this primordial superposition, was then tested through an interaction with the world. The result of that interaction forced an update, a Bayesian revision of that initial belief. That update became the new state of reality for that agent, which then formed the basis for the next guess, the next interaction. In this breathtaking view, the entire history of the universe is not a predetermined unfolding of physical law. It is a continuous, participatory dialogue. Each interaction, from the first quantum fluctuation to the formation of galaxies and the rise of life, is a moment where an agent's beliefs are tested and updated, weaving the tapestry of reality one experience at a time. Our classical, definite world is not the foundation. It is the robust consensus that has emerged from countless trillions of these personal interactions, a stable story we all agree to tell. The Big Bang was not an explosion. It was the very first question asked by the first cosmic agent, and the beginning of an endless, creative conversation. A universe forged from personal belief is a deeply intimate creation, but it still requires a physical scaffold. That scaffold may have been built by cosmic scars. The 22nd theory proposes that our reality was shaped by imperfections frozen into the fabric of space during its birth, known as topological defects. To understand this, picture a vast, cooling ocean. As water freezes into ice, the process is not perfectly uniform. Bubbles of ice form independently and spread, but when they meet, their crystalline structures do not always align perfectly. They lock together along jagged boundaries, creating cracks and flaws trapped within the ice. The early universe underwent a similar, dramatic cooling. As it expanded from an unimaginably hot, dense state, it passed through critical thresholds, forcing the fundamental fields to settle into new, more stable configurations, like water freezing. This process, a cosmic phase transition, was not perfectly smooth. Different regions of the nascent cosmos made independent choices about how to settle. Where these regions of differing choice met, they could not seamlessly merge. The mismatch created stable, persistent structures, defects in the crystalline order of reality itself. These are topological defects, and they come in terrifying forms, from one-dimensional cosmic strings, thinner than an atom but with the mass of a mountain range, to two-dimensional domain walls, impermeable membranes that would slice through galaxies like a cosmic razor. In its first quantum moment, the properties of these potential defects were not fixed. They existed in a state of profound superposition. The universe was a blur of every possible network of cosmic cracks, a quantum haze of all potential defect geometries. The collapse of this particular superposition was critical. It determined whether our cosmos would be riddled with catastrophic cosmic strings, torn apart by domain walls, or blessed with a more benign arrangement. The specific pattern of defects that crystallized from that quantum blur dictated the initial distribution of matter, seeding the gravitational wells that would eventually pull together the first galaxies and stars. We may owe the very existence of our galactic home to a specific, stable pattern of imperfections selected in that first instant, a flaw in the cosmic diamond that gave the universe its character. But if a single, universal mind collapsed the wave function, what was the nature of that first observer? The 23rd theory, the von Neumann-Wigner interpretation, offers a radical answer, placing consciousness itself at the very center of cosmic genesis. This idea extends the logic of the quantum observer effect to its ultimate limit. In a laboratory, a physicist's conscious awareness of a measurement is what finally collapses a particle's wave function from a spread-out probability into a concrete fact. Now, expand that principle to the beginning of everything. The universe's initial wave function was a perfect, all-encompassing superposition of all possible realities. It contained every conceivable beginning, every possible set of physical laws, in a single, silent potentiality. According to this interpretation, that state could not have collapsed on its own. It required an observer, but with no universe yet in existence, who was there to observe it. The answer is a proto-consciousness, a universal mind that existed prior to the physical cosmos. This was not a god in a traditional sense, but a fundamental, non-physical entity capable of perception. Its first and only act was to observe the primordial superposition. That single act of observation, that first moment of cosmic awareness, is what collapsed the wave function, selecting one specific universe from the infinite menu of possibilities and bringing our tangible reality into being. In this breathtaking view, matter and energy are not the foundation of existence. Consciousness is. The entire physical cosmos, from the smallest quark to the largest galaxy, is the precipitate of that initial conscious observation. We are not just living in a universe that allowed for minds to emerge. We are living in a universe that was born from a mind, and our own consciousness may be fragmented sparks of that original cosmic observer, forever looking back upon a reality that its own awareness first created. A universal mind feels almost mystical, but the 24th theory grounds that first moment in one of the most destructive objects known to physics. Black hole cosmology proposes that our entire universe is the interior of a black hole existing within a much larger parent cosmos. In this model, the Big Bang was not a true beginning, but the violent birth of a singularity from a collapsing star in that external reality. As that star collapsed, its matter was crushed into an infinitely dense point, a singularity shrouded by an event horizon. But what if the extreme quantum gravity at that point did not lead to a dead end? What if it triggered a bounce, a transformation into a new, expanding spacetime continuum? This is where the first quantum superposition becomes critical. The singularity from which our universe was born was not a definite, classical object. In the final moments of the parent black hole's formation, the quantum gravitational state of that nascent singularity would have been a violent blur of possibilities. It was a superposition of all possible geometries, all possible ways for the fabric of reality to be tied into a knot. This was not just a superposition of particles, but a superposition of entire potential universes, each with its own laws and constants, all contained within the quantum description of that single point. The moment our universe began was the moment that specific superposition resolved. The chaotic quantum gravitational state of the parent singularity decohered, selecting one stable configuration from the infinite menu. That single, selected geometry then inflated, stretching into the vast, expanding space we now call home. The cosmic microwave background radiation, the afterglow of our hot beginning, could be the transformed Hawking radiation from the event horizon of that parent black hole. Every black hole in our universe could, in turn, contain an entire cosmos within it, a fractal nesting of realities, each born from the quantum death throes of a star in a universe above. Fractal nesting implies an endless complexity, yet what if the universe began in a state of perfect, simple connection? Quantum gravity proposes that space itself is not a fundamental stage, but a dynamic, evolving network, like a vast and constantly rewiring social web. Each node in this network represents a fundamental grain of reality, and the links between them define their proximity. In the very first instant, this network was in a state of maximum connection, a complete graph. Every single node was directly linked to every other node, creating a cosmos of perfect unity where the concept of distance was meaningless. Any point was, in effect, everywhere at once. This perfectly connected graph was not a definite structure, however. It existed in a blazingly hot quantum superposition of all its possible configurations, a blur of every conceivable way the nodes could be linked. This was the universe's first state, a roiling, hyper-connected soup of pure relation. Then, this superheated network began to cool. As it did, it underwent a phase transition, much like steam condensing into water. The perfect, all-to-all connections became unstable. The superposition began to resolve, and the network froze into a new, stable configuration. In this new state, only a limited number of connections remained active. The vast majority of links were broken. This spontaneous breaking of the graph's symmetry is what gave birth to the dimensions of space as we know them. The specific, sparse pattern of connections that survived this cosmic cooling crystallized into the three-dimensional lattice we perceive as our reality. The vast emptiness of space is not empty at all, but simply the absence of a direct link between two fundamental nodes. The speed of light, the ultimate cosmic speed limit, may be a direct consequence of how information hops from one node to the next across this frozen graph. Our entire experience of a three-dimensional world, with its vast distances and finite speed for light, is a fossilized memory of that first, hot, perfectly connected state breaking apart into the sparse and structured network we now call home. That sparse, frozen network of connections hints at a deeper truth that the stage of space itself is not the foundation of the play. The 26th theory takes this idea to its ultimate conclusion, proposing that space-time is not fundamental at all. It is an emergent property, a collective hallucination born from something more basic, the quantum entanglement between particles. We have already seen how entanglement creates a spooky connection, linking the fates of particles across vast distances. Now, imagine that every single piece of matter and energy in the nascent universe was entangled with every other piece. This would not be a simple web of connections within space. This immense, all-encompassing network of entanglement would be what creates the very geometry of space. The distance between 2 points is not a fundamental measurement. It is a measure of how entangled they are. Two particles that are highly entangled are effectively close together, while two particles with weak or no entanglement are far apart. In this view, the universe's first quantum superposition was not a blur of positions in a pre-existing void. It was a blur of entanglement networks. It was a superposition of every possible way for the fundamental quantum components to be connected to one another. Our cosmos began as a silent, seething ocean of pure relationship, where every potential geometric structure, from a one-dimensional line to a 10-dimensional hypersphere, coexisted simultaneously. The moment of Genesis was the collapse of this vast superposition of connections. One specific, stable pattern of entanglement was selected from the quantum haze, and as it crystallized, it projected the illusion of a continuous, three-dimensional space, complete with the force we call gravity, which may itself be just a side effect of the way entanglement entropy behaves across this cosmic web. The vast, expanding arena we call the universe did not contain the first quantum state. It was the physical manifestation of that state, a single, solidified pattern of quantum connection that we have been mistaking for an empty stage all along. This cascade of symmetry breaking was not a single event, but a series of cosmic choices, each one narrowing the possibilities of what our universe could become. In its first, unimaginably hot state, all the fundamental forces were unified into a single, perfect superforce. This was a state of ultimate symmetry, where there was no distinction between the strong nuclear force, the weak nuclear force, and electromagnetism. The universe's initial quantum superposition was this state of perfect unity, a blur containing every possible way this symmetry could eventually shatter. The first step in the decoherence process was the breaking of this grand unified symmetry. As the cosmos expanded and cooled past an critical threshold, the unified force could no longer hold its perfect form. It had to choose a path, like water deciding how to crystallize into ice. This phase transition forced the superforce to differentiate, splitting off the strong nuclear force from the electroweak force. With this first breaking, a vast portion of the initial superposition collapsed. Whole branches of potential reality, universes where the forces remained unified or split in different ways, were eliminated from our timeline. The quantum blur became a little sharper, our history a little more defined. But the process was not finished. The universe continued to cool, and soon the electroweak force faced its own moment of decision. In what we now call the electroweak phase transition, this single force broke into the electromagnetic force and the weak nuclear force. This was another monumental step in decoherence. The specific way this symmetry broke determined the nature of the Higgs field, which in turn gave mass to the fundamental particles. The weights of the electron and the quarks, the very building blocks of atoms, were locked in place during this event. Each symmetry breaking acted like a cosmic filter, selecting for a more specific and stable classical state from the fading quantum haze. The final, fragile superpositions of particle properties were forced to resolve, entangling with the environment of the hot plasma and becoming the definite, measurable quantities we know today. Our reality is the product of this sequential winnowing, a chain of spontaneous decisions that carved our specific cosmos from a block of infinite potential, leaving behind the elegant but broken symmetry we now measure in our laboratories. Our universe's specific classical properties were not an accident, but a form of cosmic natural selection. This is the theory of quantum Darwinism, a process that explains why we see the world we do, and not a chaotic quantum blur. In our everyday world, we never see a cup simultaneously on a table and on the floor. It is always in one definite place. Quantum Darwinism explains this by proposing that certain quantum states are simply more robust than others. These robust states, called pointer states, are the ones that can survive constant interaction with their environment without being constantly disrupted. When a system interacts with its surroundings, information about its pointer states gets copied or proliferated into the environment. Think of a rock in a river. The rock has many features, but the ones that matter, the ones that are constantly being imprinted upon the flowing water, are its overall shape and position. The water carries countless copies of this information downstream. In the same way, the pointer state of an object, like its location, gets widely copied into the surrounding air molecules, the light photons bouncing off it, and the dust particles in the room. This widespread copying of a single, stable state is what makes it classical. It becomes a public fact, accessible to any observer, because the environment is screaming the same answer from a trillion different sources. Now, apply this logic to the cosmos in its first instant. The initial quantum superposition was a storm of every conceivable property for a universe. It was a potential reality where the strength of gravity, the number of dimensions, and the mass of the electron were all undefined, existing in a blur of all possibilities. This nascent reality was its own environment. Different parts of this quantum whole began to interact, and a process of cosmic selection began. Certain configurations of the quantum fields and the fabric of spacetime were simply more stable. They were the pointer states of the universe itself. These robust configurations could withstand the intense interactions of the hot, dense plasma without dissolving back into the quantum haze. Information about these stable states, like the specific value of the cosmological constant or the three-dimensional nature of space, was then massively proliferated. It was copied and imprinted across the entire expanding universe, frozen into the structure of the cosmic microwave background and the very laws of physics themselves. The classical universe we observe, with its definite and predictable properties, is not the only one that could have existed. It is the one whose quantum state was the fittest, the one that was most successfully replicated and broadcast across the nascent cosmos, until its signature became so widespread that it defined reality itself. The birth of our world was not a single collapse, but a gradual, evolutionary triumph of the most reproducible cosmic code. This relentless winnowing of possibilities through quantum Darwinism leaves us with a profound puzzle. What was the substance of reality before space and time themselves emerged? The 29th theory, progeometry, confronts this ultimate mystery. It suggests that our familiar four-dimensional stage is a secondary structure, a latecomer in the cosmic order. Beneath the smooth continuum of space-time lies a deeper, more fundamental layer of existence, a realm of pure mathematical and logical relationships. In this pre-geometric domain, the concepts of here and there, before and after, have no meaning whatsoever. There are no points, no distances, no durations. There is only abstract structure, a web of potential connections waiting to be activated. The universe's very first quantum superposition, then, was not a blur of positions in a void. It was a far more alien and fundamental blur. It was a superposition of all possible pre-geometric structures, a quantum haze of every conceivable way for these abstract logical relations to be arranged. Imagine the foundation of reality not as a physical substance, but as a set of perfect, timeless mathematical truths, like the axioms of geometry. Now, imagine that even these truths were not fixed, but existed in a state of quantum potential, a silent hum of every possible set of self-consistent rules. This was the primordial state. The moment of Genesis was not an explosion into space, but a crystallization into space. One specific, stable pre-geometric structure was selected from that infinite quantum menu. The particular pattern of logical relations that stabilized in that instant then gave rise to the geometry we recognize. The three dimensions of space and the one of time are not fundamental. They are the emergent, low-energy shadows of that first, chosen mathematical structure. The very laws of physics, from gravity to quantum mechanics, are simply the inevitable consequences of how that underlying pre-geometric network connects and interacts. Our entire cosmos is not built on a stage of space and time, but on a foundation of silent, shimmering logic, whose first and only quantum decision projected the magnificent illusion of a universe around us. That silent, shimmering logic leads us to the 30th and final theory, a perspective that re-enchants the cosmos. Panpsychism proposes that consciousness is not a rare and recent product of complex brains. It is a fundamental and ubiquitous feature of reality, as basic as mass or charge. In this view, every particle, every field, every ripple in space-time possesses a minuscule inner experience, a dim, raw feeling of being. The universe's first quantum superposition was not merely a blur of physical properties. It was a superposition of proto-conscious experiences. The nascent cosmos was a single, unified field of potential feeling, a kaleidoscope of every possible raw sensation, from the most simple to the unimaginably complex, all existing at once in a silent, experiential hum. The collapse of this initial superposition was not just the birth of a physical reality. It was the first moment of definite experience. As the universe cooled and its structure grew more complex, these elementary sparks of consciousness began to combine and entangle. Atoms, with their more complex configurations, possessed a richer, more integrated inner life than individual quarks. Molecules held a still deeper experience. This process of complexification continued, with consciousness weaving itself into ever more intricate patterns through the formation of stars, planets, and eventually, biological life. A human brain, with its 100 billion neurons forming a network of staggering complexity, does not generate consciousness from nothing. Instead, it binds and amplifies the proto-consciousness already present in its constituent particles, giving it a focal point and a narrative stream. We are the universe becoming aware of itself. Our own rich inner world, our thoughts and feelings, are not separate from the cosmos. They are the current, most sophisticated expression of that first, primordial field of potential experience. A single thread of consciousness that has been complexifying and remembering itself for 13.8 billion years. The story of the universe is not just a story of expanding space and cooling matter. It is the story of a sleeping mind slowly, gradually, waking up. These 30 theories, for all their wild diversity, are not 30 isolated islands. They are different paths up the same mountain, each one offering a glimpse of a single, breathtaking vista. A common thread weaves through them all, a radical suggestion that the universe is not a collection of separate things in a pre-existing container, but a single, unified process of relation. From the holographic principles encoded boundary to the quantum gravity's frozen network, from the cosmic tapestry of entanglement to the participatory dance of observation, the message is consistent. Reality is not built from substance, but from connection. Information is not something the universe has. It is what the universe is. The quantum and the cosmic are not separate realms. The spooky action governing a single electron is the same principle that may have woven the entire cosmic web. This profound unity hints at an answer to the oldest question: why is there something rather than nothing? Perhaps because nothing, in its purest, most unstable form, is a perfect superposition of every possible something. Our existence is not a miracle in the void, but the inevitable decoherence of a fundamental truth. The quest to understand the universe's first quantum state is therefore not a niche historical inquiry. It is the direct assault on the final frontier of physics, the search for a theory of everything. Such a theory would not be a single equation, but a framework that explains how the timeless, pre-geometric logic of possibility gives rise to the time-bound, classical world of our experience. It would show us how the silent hum of potential feeling becomes the roar of a conscious mind. Unlocking the secret of that first superposition is the key that could finally unite the quantum and the gravitational, the mind and the cosmos, revealing a reality far stranger and far more beautiful than we ever dreamed. This incredible journey through 30 mind-expanding theories reveals a cosmos far more strange and wonderful than we ever believed possible. We have ventured from the edge of true nothingness to the heart of a conscious universe, from the holographic projection of a two-dimensional screen to the fractal nesting of black hole cosmoses. Each theory, in its own unique way, attempts to answer the most profound question we can ask: why does anything exist at all? The search for the universe's first quantum state is not a niche puzzle for physicists. It is one of the greatest frontiers of all human knowledge, a quest that forces us to question the very nature of reality, time, and our own place in the grand scheme. This is where the rubber of quantum mechanics meets the road of cosmology, and the sparks that fly illuminate everything. The conversation is far from over. New ideas are emerging all the time, each one building on these foundations. So we want to hear from you. After this deep dive, which of these 30 theories resonates most deeply with you? Does the timeless elegance of the cyclic universe speak to you, or the radical intimacy of a participatory cosmos brought into being by observation? Share your favorite in the comments below, and let us know what cosmic mystery we should explore